Hi, I'm Jordan. In this Abaqus tutorial, we'll be covering a heat transfer problem to determine the temperature drop across an insulated pipe. Consider a thin cylindrical pipe with steam flowing through it, insulated by a thick layer of wool. The steam has a temperature of 320 degrees Celsius, and the temperature of the surrounding environment is 5 degrees Celsius. The conductivities of the pipe and insulation are 80 watts per meter Kelvin and 0.05 watts per meter Kelvin, respectively. Additionally, the heat transfer coefficients are 60 and 18 watts per meter squared Kelvin for the pipe and insulation. Using Abaqus, we look to find the temperature drops across the pipe shell, that's from R1 to R2 in the diagram, and the insulation from R2 to R3. As usual, we want to compare our Abaqus result with an analytical solution. To obtain this, we consider the thermal resistances of each region as shown in the diagram. The value of each of these can then be computed with the following expressions. Summing everything up gives us the total thermal resistance across the cylinder. We can now calculate the rate of heat loss to the surrounding environment. Computing the temperature drops across both the pipe and insulation gives 0.0229 degrees Celsius for the pipe and 283.59 degrees Celsius for the insulation. And we can also plot the temperature as a function of radius for comparison with Abaqus later on. To carry out this heat transfer analysis, we'll create two parts, one for the pipe and one for the insulation, and then define thermal materials for both of those. Then we'll consider several constraints that govern the interaction between the pipe and insulation, as well as those with the steam and surrounding environment. We'll be looking for a steady-state solution, and finally we'll cover a few post-processing tips, including how to generate an animation and how to plot the temperature as a function of radius. Let's open up Abaqus to begin the analysis. We'll start by creating the pipe, so click on Create Part and rename the part to Pipe. We're making a 2D deformable shell, and let's set the approximate size to 1. Now select the circle tool and we'll draw the pipe inner surface. So enter the origin for the center point, and for the perimeter point, enter 0.025, 0. For the outer surface, we can again enter the origin as the center point, and the perimeter point is at 0.0275, 0. Now click X at the bottom, and then Done. Now create another part for the insulation. And draw the inner surface centered at the origin and with a perimeter point of 0.02750. And then the outer surface has a radius of 0.0575. Next, we'll create a datum plane, and this is mainly for a plot of the temperature as a function of radius later on. So click on the datum plane button and then select XZ plane and leave the offset at 0. Then click on Create Partition and choose Face and Datum Plane. Then click on the datum plane and then Create Partition, and then Done. We'll do the same thing for the pipe. So we create another data plane with an offset of 0. And then click on Create Partition, Face, use Data Plane, select the data plane, create the partition, and then click Done. Now let's move to the Property module and click on the Create Material button. Type in the name Pipe Material and then select Thermal and then Conductivity. Then enter 80 for the conductivity and click OK. Now let's create a section by clicking on the Section menu and then Create. And we're creating a solid homogeneous section here. And you can leave plain stress or plain strain thickness as 1. Then assign the section by selecting the entire pipe and click down at the bottom. And click OK. Now let's create the insulation material. And the only difference here is that we have a conductivity of 0.05. Now create the section. Select the insulation material. And then finally assign the section to the insulation part. Now let's move to the assembly module and create an instance. When the box pops up, click on both parts and select them. You can do this using the Shift tool. We'll use a dependent instance and then click OK. Now we want to create the step. Select Heat Transfer in the bottom menu and then continue. Under Response, select Steady State, and you can dismiss the box that pops up here. In the Incrementation tab, let's enter an initial increment size of 0.01. This will force Abaqus to take multiple steps towards the solution when solving, and because of this, we'll be able to create an animation later on. In the interaction module, we want to set up a few surface interactions, but this will be much easier if we've created surfaces beforehand. So let's go back and expand the parts in the model tree. And then under insulation, let's right click on surfaces and create the inner surface. So type in a name, click OK, and then select the regions for the inner surface of the insulation. Then let's do the same thing for the outer surface. And you can select multiple regions by holding down the Shift key while clicking. Now we'll do the same thing for the pipe and create two surfaces, starting with the inner surface, and then we'll do the outer surface. After we've created these 4 surfaces, move back to the interaction module. Click on the Create Constraint button. Select Type Tie, and then click Continue. Choose Surface at the bottom for the master type. And at this point, it'd be tough to pick the outer pipe surface. So click on Surfaces in the bottom right of the screen. And since we created them before, we can now select the outer surface of the pipe like this. Then at the bottom, for the slave surface, select the inner insulation surface, and then continue. Now here we'll specify a distance of 0.001 for the position tolerance, and uncheck Adjust Slave Surface Initial Position. Then click on Create Interaction. We'll start by creating the interaction for the insulation outer surface. So click on Surface Film Condition, and then Insulation Outer Surface. Enter a film coefficient of 18, and then a sink temperature of 5. Create another surface film interaction for the pipe inner surface. And enter 60 for the film coefficient and 320 for the sink temperature. There aren't any loads to be applied, so let's move to the mesh module and start by meshing the pipe. We'll assign global seeds with an approximate size of 0.0005. After clicking OK, go up to the Mesh menu at the top and select Controls, and select all the regions and then Done at the bottom. We'll click on Quad and Medial Axis. Then go to Mesh and Element Type. Select the regions and change the family of element to Heat Transfer, and then click OK at the bottom. Now we can mesh the part. So click on Mesh Part and then Yes at the bottom. Switch over to the insulation part, and we'll carry out more or less the same procedure as we did for the pipe. So we'll assign global seeds of 0.005 this time, and then go into Mesh Controls and use the same options as we did before. The medial axis algorithm generally works better for parts with circular geometries. Let's finish up meshing this part. And then once we've done that, we can move to the job module and create a job. we'll rename the job, then click on Continue. And we can leave the Edit Job box as it is and click on OK. Then open up the Job Manager. Make sure the job we created was selected, and then click on Submit. And don't worry about this box that pops up here, we can ignore that. Once the job is completed, click on Results, and if we click on Plot Contours onto Form Shape, we'll see the heat flux magnitude. If you want to change to the temperature, choose NT11, and we can see that the max temperature is just over 300 Celsius, and the minimum temperature at the outside of the installation is roughly 23. By clicking on the Query tool, we can probe values at any node. The result we really want is the temperature plotted against the radius. So click on Tools, Path, and then Create. Make sure Node List is selected, and then click on Continue. Then zoom in towards the inner radius, and click on Add Before, and then select the start and end points of the path. Then click on Down at the bottom, and then OK. To plot, we'll go back to Tools, XY Data, Create, and select Path, and then Continue. Now if we click on Plot right now, we'll get a linear plot that shows the temperature at the pipe inner radius and at the outer radius of the installation. To get all of the points in between, we need to click on Include Intersections, and then plot again to regenerate the plot. Now this result looks a lot like what we had in the introduction slides for the analytical solution. Let's take a brief aside and go through how to create an animation, and then we'll come back to verify the results. So I'll click on the Plot Contours onto Form Shape button, and then click on Animate Scale Factor to get this animation displayed. Depending if you're doing a dynamic analysis or something else, you can animate using one of the three buttons that are near the cursor. Finally, to verify our results with the analytical solution at the beginning, we'll go back to the plot we created. And a couple other things, you can change the XY axis options by clicking on this button. And this contains things like font sizes for the title, tick marks, line widths. So we won't change anything here, but this is where you would change it if you wanted to. You can also click on the curve options button and again change things like line width or add legend text. Finally, we'll use the Query tool to probe values at the inner pipe radius, outer pipe radius, and at the outer radius of the insulation. So comparing these values with those obtained from the analytical solution, we'll see that they essentially match. plot of the temperature as a function of radius also matches the analytical solution. That's all for this video. Thank you for watching.